Gasp. How are we doing? Wanted this to already be going, but Steam decided it wanted to update. Oh, we don't need music for this. Wait. Hey. That's the... Isn't there a continue? Okay. That's the shortcut. Oh, maybe it's in here. I don't remember. I'm too old for this. I could have swore I had a save. Well, fresh level 1. How we doing on this beautiful Thursday? Oh god. Everybody doing well? Really? Really? Mind a heart about now. was lucky. Right into the whatever you are. Heart. Have heart. Eh. 5 minutes till class. Seems like a fair amount of time to me. Hey, 1 heart. Ooh, level up. What do you do again? Okay, that's right. Whee! Now we're just fooling around. Makarov. We have a blue chest. No, these are the rat boots. Yes. Which means this is gonna be a gun. Ooh, Cupid's charmed bow, that's right. So I think this one I can walk on here. Is that right? Okay. That's... Ooh, this guy's not too bad. Yeah, I forgot to do so. Come on. Precious time we could be not dealing with that. Grr. Hey there. Oh god, reaction time is so bad. Look here, look here, look here. That was awful. 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 I'm mad about that one. Oh god. Oh well. Alright, go away, Gungeon. I love the bullet's the most fun. Honestly, I do better with the bullet than I do with any of the other ones. He said as he dies horribly every time. If I ever do a stream for fun, which I haven't had time for much of those lately, but I'll do a little Gungeon. Enter the Gungeon. It's one of those roguelikes. No, it's a roguelite, sorry. Gun-based. It's a game where you can play as a bullet who has a gun that shoots more guns. It's pretty fun. I like it. If you're into the whole Binding of Isaac type of gameplay, that's like a... the combat feels very solid and rewarding, I suppose. I picked up a few other games. So I picked up the new Humble Bundle, the story-based games one. Your cam froze. We okay now? Should be good. Can you see me? Or maybe the whole screen. Looks fine to me. Okay, that's good. Could be when I closed off the game. Might have done something funky. So anyway, I picked up the new bundle. It's like a story-based game. Story-based game, narrative-based games. It's kind of interesting. Just to throw a few out there. Let's see if I can find Humble. Not trying to like advocate for any of these, but I figured I'd step outside of my comfort zone. Reven Revenger. So these are all like story-based games. Obviously, here's Monkey Island. That's not strictly story, but there's some interesting ones in here. Like this one kind of reminds me of those Until Dawn type of games, but it's a 40s era noir, except everything's an animal, which is kind of interesting. Play Hollow Knight. I do have Hollow Knight. I got about halfway into it, and I didn't get bored. Just Trying to remember why I stopped playing that one. Hollow Knight's fun. It's gorgeous. I love the environment, but Metroidvania gameplay has to have, to me, the mapping. I think it was the mapping system that irked me. Hollow Knight. Hollow Knight is a good game. Yeah. Should go through my Steam library one of these days and take requests. What do we got here? Reven Revenger. This is interesting. I threw this one out there on Discord in the CIS one the other day, Kingsway. It's like a Windows 95 era roguelike game. It's hilarious. Haven't beaten it, but yeah. Excuse me. Okay, probably enough game talk. Did you ever get into Heroes of Might and Magic? Thank you. You're so sweet. Um, I So that's an interesting one. I've always wanted to get into it. And I finally picked up, they had a bundle recently with like all the old Heroes of Might and Magic games on. I think it was GOG. Ooh, Lisa. Yeah, did you see that in my list there? That's a game. That's an interesting one. I think Lisa was actually I think it's an RPG Maker game, if I remember right. But Heroes of Might and Magic, I downloaded it and I couldn't get into the interface that they had. So I figured I would hold off until I go through all the upgrades and maybe give it its proper due over the summer or something like that. Lisa is a very dark game, I will say that. I got through most of the first one. I never did the expansion, though I think I have it. Okay, we should probably talk class stuff though, right? Just go straight to Heroes 3. That's the one that I was planning on. Is it in Steam? No, it's got to be in my GOG account. What else do we have? Okay, it's coming from elsewhere. Noita, this is a gorgeous one. Every pixel does something. Check out some Noita videos if you haven't. It's insane. All right, we ended here about, I would say, right? Okay, yeah, where's my little note? Ended here, okay. We're into the abyss. I was into Grim Dawn for a while as well. I don't know if any of you are into like the Diablo style ARPG type of game, but that was a very solidly put together one. And I think somebody made a mod that actually turns it into Diablo 2, which is now getting a new beautiful reorientation, or release. So excited about that. All right, today I'm going to be messing around with my camera a little bit. So I've got a blackboard here, or I've got my kid's whiteboard. Got sucked into the screen and I'm not even in this class. Perfect. No worries. So this is about where we ended up. We started talking about arrays. Yeah, the tablet was driving me nuts. If we sub, will you put our name on it? That's only for people who. That's the. I don't do Twitch too much outside of class, but that's if you gift a sub to somebody or something, right? But yeah, let's see. There, tier 1 perks. Nailed it. For a hot moment, I thought it would be fun to do like a charity type live stream thing, playing games for something, but I couldn't get any other faculty interested in it. I know, I got rid of all that stuff because I don't want this channel monetized. Be a little ethically weird. Anyway, kind of the point I want to get to here. Let me know if you can all see this okay. So we have a square, all right? So we got point here, and these are two triangles, right? So just making sure that comes through okay, except some white balancing going on. Okay. So if we know that this is x1, y1, my font's probably way too small here. Let me try to make this bigger. X1, y1. Okay, I'm gonna say this is x2, y2. If we want to draw a square, one of the things that we have to worry about, let me, I'll probably, let's do this. Awesome. Now watch me trip over that. So again, we want to, what we're trying to accomplish here, and I kind of skipped over why I'm doing this whole example, is that we're trying to draw a square with only two vectors. So we're kind of trying to minimize the amount of points that we keep track of, right? So if we know this is x1, y1, this is x2, y2, and we want to figure out where the triangles are, basically what I'm saying is we can draw a square with 2 points. We're just going to extrapolate here. So if I need, these vertices to push onto my array buffer, this is very clearly x1, too small, x1, y2, right? And then this is going to be x2, y1. Because let's say we're on our, our x-axis here. I should be doing this in red so that we can see a little bit of a different color. So this is obviously x, this is y in this case. Kind of the point here is this is the basis of some of those like triangularization algorithms where we're basically just figuring out where we're putting points, and we can then figure out where everything else goes. And in this case, since we are doing square objects or rectangular objects, we can just kind of say, okay, I want a point here. Let's automatically figure out where the other two vertices are. So let's go back to smaller me, and it's probably going to be slightly offset from my background. Oh, not too bad in this one. But this is kind of where we left off last time. We are pushing to the other two triangles. We are automatically generating our points, and this is very, very simplistic here, right? So very easy to figure out offsets for other vertices. This is going to get into, let's see, I don't have a good example right here, but if we're going to be figuring out where different vertices of our triangles are, we can kind of extrapolate a little bit more of a complicated algorithm, right? Some of your geometric identities from way back when we can use to figure out points like this. Like if I want to say, let's draw an equilateral triangle right here, I can figure out where all the other points are just by a few geometric identity problems, right? And this isn't really the class where I'm going to test you on what those are, but just kind of the key is that you can generate objects with very little knowledge. So really here we only have 2 points, and we can figure out where the other two are for this square or this rectangle. And if you don't remember what I'm talking about in the least, this is that CAD1 example. So click, click, draws a rectangle. Click, click, draws a rectangle, right? We're giving it 2 points, it's figuring out the other two. It is extrapolating. So let's see, this function, so we're talking about the CAD applications in our little example here. So we are recording the location of our click. We're getting another click. We are indicating to the application that we are done. We are ready to push a new square into our buffer. We're going to figure out those other vertices, and we're going to push everything to our overall array buffer. And if that's a little bit obtuse, I can show you here again just so that you remember. Every time we click in this CAD1 example, same for CAD2, we're going to get the x and the y. And again, we did that little, not a trick, but we updated our x and y functions with this bounding rectangle. We're going to set our vertex for the first one. We are going to set our vertex for the second one. So T1 and T2. This is the same as our, well, this is T0, T1, T1 and T2 basically. We figure out what the other two are, and then we're going to do some indexing. Now, this is where we start talking about things in JavaScript land which don't normally make sense, or doesn't normally make sense for us. We have to be concerned with things like bytes and indices you have, but basically these objects that we're creating have a amount of memory. And if you see this 8 times index plus 1 plus 2 plus 3, and then later on 16, 16, 16, this is because we're saying that there are basically 8 bytes that we have to deal with per vertex. Okay, so 8 times index, if this is index 0, the offset is 0. If the index is 1, we are 8 bytes offset into this array. So if you are familiar with the ugly C, C++ days of actual low-level memory management, you should feel right at home here. If not, a vec2 is basically 8 bytes. That's what we're going to be worried about here. Extrapolate. When we talk about colors, we create vec4s. So those are going to be 16 bytes, right? For a single point, all we need is 8, right? 8 bytes. For a color, we need 16 bytes. And then again, we're just going to index into this array with some offset. And can be slightly annoying / confusing to look at in this particular regard. But again, all we're doing is indexing into this big array buffer that we've created. And that's where this buffer subdata function comes in. Right before, it's just been straight up so GL buffer data, right? That's all we've been using so far. In CAD1, if you've looked at it at all, you see 16 times the max number of vertices for color, 8 times the maximum number of vertices for the actual locations for the positional data. This is basically saying 8 bytes per vertex, here's how many vertices we are going to support. Anything above that is going to blow our vector out and we're not going to support it anymore. So this takes us to a bit of actual buffer interactions. So each of our clicks, we're going to update a pointer or an index into this array. And later on, we're going to tell it to draw triangles based on where it is in this array. So in this case, differences here that you should notice when I'd also recommend playing around with CAD1 and CAD2 to really see what's going on and kind of tease it apart. You're not just drawing one buffer, you're handling basically sub-entries into the buffer, which means we're getting multiple shapes at different locations in our overall frame buffer. Okay, so buffer subdata lets us work with those directly. The other thing in here too is if we skip down to the bottom in our render function, we're not just calling gl.drawArrays once, we're calling it in a loop. So what's happening here is that we are saying draw a triangle fan index %for a number of times. Any idea why we're doing multiple draw array calls? So again, here we are working with our CAD application. So when this is being rendered, again, this is being rendered in a loop. It's not being rendered one big object. Why would we be doing that? This a question makes sense, I guess. Why is draw arrays in a loop here instead of by itself? I've got more drawing to do. Oh god! This is very precariously perched on a little IKEA table. All right, so the question is relating to this line here. Any guesses? Or are we all lost? Is it because we want to draw all of our squares? Yes, we want to draw all of our squares and we want to draw them separately. Okay, so if we take a look at this thing here. If I drew this all at once, this would be one big amorphous object, right? So let's actually do, let's see if I can not break this. Yeah, exactly. So if I do gl.draw arrays, gl.triangle fan, I've not done this, so if I screw this up, that's why. And we want to do 4 times, no, we want to do index. I think that's what we want. Yeah. See if I can break this now. Yeah, we get something horrible like this. Although the shading comes in nicely. Actually, I have a nice little 3D effect going on here. But this is a triangle fan, right? So we have a singular starting point. Wow, that's actually kind of trippy. I like this. Was not expecting that. It's like a cyberpunky tunnel type of thing here. Cool, I like this. Um, so if we have it just drawing everything at once, it's going to art, yeah. I like whoever posted in the chat that this is clearly an art class now with my awful stick figures. Um, but we are treating this as a single shape, right? So the triangle fan rules will apply here. Single point, and then all the other vertices will go back to that first point. Whereas, if we are here, every single time we will draw a single triangle fan, and as you see based on the way this loop is set up, right, I equals 0, I is less than index, I plus equals 4, and then we're going to index into our buffer from the current place to the current place, basically plus 4. Right, so we're getting those 4 vertices in there to get our actual rectangular shape. And you could take this and honestly extend it if you wanted to see, we could put as many polygons as we want that our buffer can hold, and we can just treat them all as separate objects. These are just indices into an array. But the key here is that you have to know where in the buffer your various polygons are. Okay, so here it's easy. Everything's a rectangle. But what if you had a rectangle, then a triangle, then a circle, then a duck? Okay, you're going to have to keep track of where those boundaries are, and that's going to be up to you in your application. But yeah, it's kind of like that pipe dream wallpaper almost. So yeah, basically buffer subdata is going to be helpful when you have multiple polygons going on here. Okay, and that's why we are handling that. Squares were easy. Honestly, let's take a look at polygons now. So this is the CAD2 example. Okay, so if I go to CAD2, if you remember, this was our, I'm just kind of clicking around, and then once I click end polygon, it draws the shape. So it kind of has that same effect that the last one did, except instead of, click once, click twice, and polygon, I have to click multiple times and then end polygon. Okay, so what are the differences here? Do you think we have to update our shaders at all for this? Right, so the last one, CAD1, was just squares or rectangles. You get one color per object. And I'm just going to do a quick test. Okay. I think I've got it. I think my weird headphone issues are the fact that my phone is also paired to my headset. Okay, let's do that. So, nice shading, multiple vertices versus boring old rectangles. Shader differences? Nah, no change. Still a basic pass-through shaders. Render, no change. Interesting. But there is a slight minute difference here. I should say that. So let's pop over to CAD2. So now I'm in the CAD2 code. Again, our shaders do not change. Let's pass through the position, pass through the color. Nothing crazy going on here. The application, though, we are going to have a slight bit of a difference. Now, I guess I should say our buffers that we are creating, if you're comparing CAD1 and CAD2, get rid of this here. Oh, I was told by one of my former slash current grad students that not auto-formatting code is hurting her feelings. So I think it's a Control Alt Shift F. The vi bindings also screw that up as well. So yeah, I'll look at it again later. Anyway, differences here. We may have different indices. We can't guarantee it's going to be vertex 1, 2, 3, 4. That's your rectangle. 5, 6, 7, 8, another rectangle. Okay, we're actually going to have different starting points and different ending points. So all that means is that for every polygon we have here, we're going to loop over the start, and then we're going to keep track of how many indices there are. Okay, so the way this function works, or the way this application works then, is that I'm going to have probably a 2 or more, I think it was 3 or more, because it didn't really do anything when I did 2, right? If I go back to CAD 2, 1, 2, and yeah, it's going to enforce 3. 1, 2, 3. Okay, so we need at least 3 vertices for this guy. I didn't go through and check that, so I was kind of spitballing there. But for every click, we're going to push it down. So here, if we go to our click, we're going to get our vertex. We're going to add it to our buffer. And then the little trick here is that we're going to increment the number of vertices that this particular polygon has. So this gives us the flexibility application-wise to say, okay, this is 3, this is 4, this is 5, this is n vertices for the polygon. And basically, we're just going to say how many does it have, and we're going to use that to index into our buffer. Does that make sense to you all? So basically, we're just making it a little bit more flexible here. And I'm not seeing any code in here for enforcing 3 vertices, it looks like, so I'm guessing it's just how render is set up here. Oh, it's a triangle fan. You need 3 vertices, otherwise it's not going to work. Makes sense. Perfect. Okay. So we're basically just having little lookup tables. So nice, cheap from a memory perspective. And then with that, we're going to push down the color too. So every time we click, we're going to push a vertex onto our buffer. We'll also push the color onto our buffers as well. So you have your position buffer, color buffer. Every time we click, push down blue, select yellow, push down yellow, push down magenta, and polygon, triangle with multiple colors. Again, this nice gradient effect because that's the default coloring behavior in WebGL. Again, our buffer subdata functions do not change here. We just are going to change basically what the index is. And again, vertex position, we need 8 times the index. That may be different depending on what type of objects you're rendering. Maybe you need 3-dimensional, so it'd be a little bit more than 8. Or, yeah, basically that makes sense. If you skipped ahead and saw this homework slide, we're not going to worry about this since you have your exam coming up next week. But if you want to play around with theta, it's kind of a fun little thing to do. Basically make it go faster or slower. Questions at all on the buffers, indexing, buffer subdata? Obviously, using this function is going to be helpful. We're not going to play with it too much, but mainly the concepts of indexing are important here. Would a little example on the whiteboard help you at all if you're lost at all? So I don't want to leave any point as confusing. See if I can do this. So if I want to draw a triangle, right? We can see that. Wouldn't say no. Hey, hey. So let's say this is our standard point. So we have a vec2, -1, -1. So let's say this is 0. 1 is a vec2. So we'll say that this is 0, 1. And then 2 is also a vec2. This is going to be 1, -1. Hopefully that makes sense. My cute little IKEA whiteboard here. Okay, so what this is going to look like then is that we have our giant buffer, right? So this is our array buffer. I'm just gonna assume we have assigned it. So this is going to basically, with our function or with our functions mod, our libraries that we're importing, this is going to go in as -1, -1, 0, 1, 1, -1. And let's say this is the amount of buffer space we have reserved. So it is a flat list, if you recall. And I lost my, oh, caps right here. So if I'm indexing into this thing, right, so this is 0, 1, 2, 3, 4, 5. If I want the first point, I start here, and I'm going to, well, actually, let me rephrase in the context of the example. If I want to do a draw erase call, this is going to be start at 0. You know what? Let's do one more line here. See if we can get the bottom cut off. So this is the gl.draw erase. Yes, going from small caps to all caps is not confusing to anybody, I'm sure. So this is our triangle. So I'm just going to draw a triangle. We start at 0, and it goes 0, 1, 2, 3, 4, 5. Basically, right? If I wanted to start here, let's say that this goes on for a lot longer. This could be 0 or index times 8, right? So if index is here, 0 times 8 is going to go here. Otherwise, we could do, index times 8, and we'd have the extra ones for the square. The index would start here and then go another 8 bytes past that. So kind of the key takeaway is that just get comfortable with indexing, because that's all working with that buffer is. Which one is going to stay after class to clap the eraser? That's the thing with whiteboards, right? Okay. I am huge. Let's go back to my nice comfortable corner here. All right. Before we move on to the geometry type stuff, so let's see. Got 45 minutes left. I'll probably put a little bit of this on the midterm, depending on how far we get. This is going to be about vectors and matrices. We're not going to get through the whole thing, so there wouldn't be too much on it. You have homework due tonight. Anybody have any questions on that at all? Crap, I forgot to hit record. Okay. You're getting me failing miserably at Gungeon again at the beginning of class, I guess. If you don't have any questions, we can carry on. I didn't look to see how many submissions I've had yet. Bonus content. So I'm going to assume everybody's okay with the homework if nobody's got any questions. Is our project a group project? Hey, that is a good question. It doesn't have to be. It can if you want it to be. So I'm going to say groups of probably 1 to 3, where if you're doing anything, I'll have you propose it after the midterm. But again, it's not intended to be a whole semester type thing, since I'm going to be giving you assignments along the way too, so I don't want it to be too crazy. Actually, let me pull this up because I thought this was fascinating. Oops, we do not want that to pop up there. We want this in incognito mode. So this was pretty cool. I thought I saw the posted this in the Discord channel. So here is procedurally generated canyons in Blender. Not sure if anybody saw this or not. So there you go. You have a generated desert environment for your amazing Unity game in Blender. Basically, so I didn't go into the details of how they did it. Oh, I guess there you go. Using fractals and some, I'm gonna guess, shader nodes, whole bunch of stuff, cool stuff going on. Animated canyons being formed in Blender. That's why I said you can do some pretty neat stuff directly in Blender if you want to. Why is this stuck at full screen? Yeah, thank you. I'm glad you liked that. Are you talking about the actual one or the one that I put up? I had to sneak that in there, and honestly, I don't know if anybody is watching. I think I threw that up at like 7 or 7:30 this morning. There's about 3 or 4 attempts in Discord to hide the preview because I couldn't. I kept mistyping. You surround something in angle brackets, and that hides the Discord preview. Otherwise, everybody would have seen it pop up. Okay, let's get through a little bit of geometry and transforms then. So this is going to be the most that we're going to talk about matrices and vectors outside of using libraries to handle them. Basically, this is kind of the core concepts underlying how we can do things in 2D and 3D. Mainly, we're going to consider this in terms of 3D, honestly. But this is going to be hopefully not too painful. As a forewarning, I am not going to be going into detail about matrix math or vector math. That is not something we really have to do here because we're just going to assume that you know how to do these calculations. And if you don't, we have libraries for them. So just kind of keep that in mind. Purpose is to use these identities in applications, not necessarily go through the horrible do matrix math by hand type of problem. So in terms of geometry, this is going to basically be how we can do everything that we need to do in graphics. Okay, everything we've looked at so far has been, okay, here's how WebGL does things. Here are the functions you can call. Here's a bit about the buffers and, you know, limited shaders, fragments and positions and all that fun stuff. Just kind of the key technical basics. Now we're actually going to start doing real things with our shaders. We're going to start having them actually perform some math and do some work for us. To do that, we need to understand how it handles vectors and how it handles matrices and everything that goes into that. And again, we're going to look at it at a pretty high level, and we're just going to take it and apply it to our applications. I've got a whiteboard here for some drawing. Hopefully it won't be too painful. This is one of the happiest images I could find on Unsplash to ease you into this lecture. Just a forewarning, though. Excuse me. Now, if you do have the book, Appendix B in it has detailed information on matrix math and representations. Obviously, I didn't make you buy the book. So if you need further detail, let me know and I can try to find you some references for, you know, it's kind of like the detailed geometry that you would need coming into something like this. But don't worry. The other stuff in there is like polar coordinates versus Cartesian versus some of these other coordinate systems. Anyway, let's get into the fun stuff. So on a slide or two ago, let's see, we're going to talk about math in a coordinate-free manner. And coordinate-free is basically a nice way of saying that we don't have a coordinate system. We're not specifying our locations in terms of any known way of mapping things out. Okay? So basically we have some kind of a non-physical thing that lives in a space that we don't really describe. So you're used to your standard Cartesian coordinates. These are your x, y, and z points, right? So that's your x-axis, y-axis, z-axis. And we're going to do things to these points based on this known system, right? What I'm trying to get you to think of here is that this coordinate system, Cartesian or otherwise, those of you that have gone through probably, would it be trig or one of the calcs where you get into like polar coordinates and things of that nature? These are just arbitrary systems. They only hold meaning to you and I as humans, and obviously the computers that we're programming, right? But if I'm to draw a point, say here, what does that mean? Other than I'm hiding it. So I've got a dot in red right here. How do I know where this thing is? I don't. I have no way to describe it. I could say it's right there. Now you all go ahead and replicate that in WebGL. But if you were to do it perfectly, you would need to know a coordinate system. Okay, is this X, Y, Z? Are we using polar coordinates? Are we using something else that I made up on the spot just because I wanted to prove a point? A point, and that's unintentional pun. Basically, the key here is that we can do lots of stuff to these points regardless of the coordinate system. So take, for instance, your standard vector, and this is going to be, vectors are going to be important here because vectors actually help us describe everything with our coordinate systems. Why did you shift down, but I didn't? Okay. Horrifying full image of me. So here we have, let's say I've got, I don't even want to point. We're going to start with the vector. Again, everything we're going to be doing is in terms of vectors here. So let's say that I have a vector v, okay? This vector v has a direction, has a magnitude, that's a vector. Think back to your horrible times you probably had in geometry class. We remember like the head to tail method and all that fun stuff of adding and subtracting and all that lovely types of things that we do with vectors. Okay, let's say we have another vector. Okay, I'm gonna do this here. Let's call this one W. I don't have any reason why other than let's write a little curly and a W. I remember, okay, diff EQ. It's been a while since I've done undergrad math. Couldn't remember exactly where they were. And then mixed in with engineering classes, you get reintroduced to it. So I've got two vectors. What's the difference between these two vectors? Any guesses here? They look pretty different, right? They're clearly in different spots. The starting point. But I haven't given it a starting point. That's the key. These are identical from a mathematical perspective. If I had a coordinate system, absolutely, they would be different based on their starting point. But there is no coordinate system here, meaning that we have something called confusion. Yeah, there is no difference. Assuming that my drawing skills are perfect, which clearly they are, this one even needs a little person on it. Let's do the, is that movie where he rides the bomb down? There is no difference here. Same magnitude, same direction. Even though they look different, they are exactly 100% identical. So, and what is going on here with my scaling? All right, good enough. So they might look different. Now, the key here is that they don't have any starting points. We don't have what's called a frame for this type of thing. We haven't defined a coordinate system for them. Now, one thing that we have to talk about before we get into that is this concept of dimensionality. So we'll think of dimensions in terms of 1D, 2D, 3D, things of that nature, right? The dimension of your coordinate system, of the space that your systems live in, is based on how many linearly independent vectors you can draw. Okay, so think of your right hand rule, which hopefully you have heard of before. Basically, if you point one finger in one direction, another finger in another direction, your third finger is going to go in an equal and opposite direction. These things are never going to be represented in terms of each other, okay? So if that doesn't make sense, let me give you another drawing here. Let me make me massive again. What this means is that if I'm going to draw one vector this way, I can draw, I'll just keep it all in black, another vector this way. This would be a two-dimensional space. If I want to make it 3D, it has to go this way. These are completely independent of each other, meaning that we can write them in terms of vector 1 plus vector 2 plus vector 3 equals 0. They cancel each other out. These alphas that you see on here basically are indicating their magnitudes. And this is all going to be in basically Latin, or Latin characters. Greek characters? Latin characters. Just because they're arbitrary at this point. But the key is that they will cancel each other out. Greek. Okay, thank you. I swear, 4 o'clock and beyond, brain stops working. But what we're going to call this is a basis. So this basis forms a coordinate system for us. And that's all we care about in this point, right? We see that we can base a coordinate system around this set of vectors. And why are we haranguing this point here? This representation is how we are going to represent every single object in our system. Now, this coordinate system hinges on this center point right here, right? So that's going to be your 0, 0, 0. But we haven't specified that yet. So the issue is that I could draw something like this. So let's draw 3 linearly independent vectors. I'm going to draw this one here, draw this one here, and we'll draw this one way up here. And we'll make them the same length. So this is our alphas that we've got. Again, these are identical. So this and this are the same thing. So what I'm trying to get you to think of here is that we have to be very rigorous in how we define our coordinate systems. So we're actually we're actually defining our frames of reference, and cut to Big Lebowski joke. So what these coordinate systems are getting us in terms of, the graphics world is that we are basically defining what the screen is drawing. So we are taking points that we are plopping into that buffer, and we are relating it to some object in terms of representation. So if you look at a drawing, let's say we draw let's do a nice donut. We'll draw it around the center, just because you're all going to be doing donuts pretty soon. Get that nice drizzly frosting on there, nice and pretty, maybe some sprinkles. Okay. This object is centered around the origin here. If I want to move this thing around, you can't see that now. See my beautiful artwork. There we go. Nice, beautiful donut. Oh, I gotta do the back too, sorry. It's clearly got some 3D here. This could be in relation to your eyeball. So if you're looking at something, it might look differently than it looks to a camera or to other objects in the world. And this kind of gets in with the light ray representation stuff that we talked about last time with the little Disney video. Key takeaway here is that we need this frame. This is going to help us define everything in terms of our graphical scenes. Okay, so what is a coordinate system? Again, it's a list of vectors. And with that, we're going to have some scalars. So with our vectors and our scalars, we're going to be able to really define what our system actually looks like. So the basis are the vectors. So that's your vectors going out. The scalars are going to give us the magnitude. The overall vector is the scalar times the basis, and that's our system. Okay, so if you want to easily represent a frame of reference, you can just represent it in terms of a list of scalars. And these are typically written like something equals a1, a2, comma, comma, an transposed, because normally we're going to have it in this column-based format. Sorry, this row-based format. If I've lost anybody, please let me know. Let me, let's see, is this next one here the example? Yeah. So I've got an example for you if this helps, because this is also going to get into some of our math here. Make me bigger again. We haven't made anybody sick yet. So let's say that I want to draw a vector. And this is basic vector stuff. So I'm going to say I've got, what is it? V equals 2. Actually, no, let's do it properly. Otherwise it's not going to follow those slides. So I've got V equals, is it A or alpha? Let's do alpha. Alpha 1, V1 plus alpha 2, V2 plus alpha 3, V3. And that's actually going to be a 3. Okay, so that's my vector definition. Again, symbolic at this point, right? But what I can say is that alpha equals 1, comma, let's do something interesting. Say 2, comma, 4, comma, 6, transposed, which means we're just going to flip it, like you see here on the screen. All right, so this is my list of scalars. If I'm going to translate this into an actual coordinate system, so I'm going to actually draw one out here. Okay. So this is my z, my y, my x. Assuming I have defined this coordinate system, I know how to draw this vector, right? And with this, we're going to know how to draw points and things of that nature. So a vector here, so this is going to be positive 2. So 1, 2. So this is 2 on my x. We're going to go up 4. 1, 2, 3, 4. And this is following the slides, so just so that you're aware, this is not how WebGL handles it. We're going to go 6 positive in z. But our WebGL, we have z going positive in this direction. But more commonly, z is positive in this direction. So just be aware that when you start doing WebGL and you do a positive z coordinate, it's going to go into your screen, not out of your screen. You have to transform it if you want that to happen. So what does this mean now? All right, so I've got, let's do red now. So I'm at 2. We're going to go up to 4. So we're here. And then we're going to go down 6. So see, this is something like this. Slightly off. So this is going to be where my magnitude is. And then I'm just going to draw the vector from the origin. So it's going to look like this. So this is the vector that I'm trying to describe with this coordinate system that I have defined. The interesting thing here is that this coordinate system is 100% made up. It is flexible. You can do whatever you want to this thing. And that's the basis of how we do all of our transformations in OpenGL, WebGL, and graphics in general, really. If I want this thing to rotate, right, so I want my vector to be like that, what do? I just change the frame. So I'm going to rotate this whole thing. So the points are still going to the same location in this coordinate system, just I've changed the entire frame of reference here. And the key, if I undo this, pretend it's a smartboard, go back to my donut that I drew. If I want to rotate the donut, just rotate the axes it's living on. And then that's our change. Now, the nice thing about this is that the, your drawing framework for SWebGL, but any of them, it's going to handle those vertices automatically. So we're going to tell it what the coordinate system is, and then the actual drawing of the vertices is going to be handled by the framework. Yes, that's exactly right. Every object has its own coordinates. Coordinate system, sorry. So this is the example, if you didn't want to follow what I drew out there on the board. Basically, we are going to draw some point or something. Right here, we're drawing vectors. This isn't with respect to a specific basis. An object is a loose term. Yeah, everything is a loose term here. Yep, exactly right. So let's try to maybe think here for a second. So we have a coordinate system for every object, right? And if we can manipulate the coordinate system, how do we translate it to different perspectives? So maybe I want to go from looking at it by default, which if you're familiar with WebGL this far, right, it's top down. What if I want my camera to be looking around? What do you think that means? Again, we're just transforming coordinate systems here. So this was the example that I went into earlier. These are all identical, right? So this is, again, kind of the basis of graphics, that our coordinate systems are flexible, our objects are flexible. These are the same thing that we see here. Even this frame, it's the same thing because we don't have a point to anchor it. So we are basically in a very simple coordinate space, right? We are coordinateless at this point because everything has no meaning. You need to add a point, okay? So this is where our basis vectors are going to emanate from. And we're going to go into something called the affine space. So if I want this to be an actual honest-to-goodness system that we can draw something to, I need a big fat point right here, okay? So this is going to be P0. That is our origin. Okay, that's 0, 0, 0 for us. Intuitively, everything you've ever learned in class so far, that was probably a given, right? You never had to question that the center of your axes was 0. But when we're getting into graphics land, this doesn't exist until you tell the computer that it exists. And obviously WebGL, your different frameworks are going to help you with that. But kind of the core of how we do things is that this is not a reality. We're kind of creating it ourselves. You could create your own coordinate system. Graphics land, patent pending. Yep, it's the name of my new Twitch channel, Graphics Land. Make sure you like, comment, and subscribe, and ding that bell. That's where we talk about graphics all day, every day. So once we have a basis and we have an origin, this is called a frame. So then how do we describe a frame? It's those three vectors that we had before, add on P0. So basically it's going to look something like this. And with this formula, you can describe any frame. You define your origin within an existing frame. Basically, yes, you can do that. Yeah, so we will have different frames for everything. You can copy them if you need to, absolutely. Okay. It will become clear. Honestly, this is the more theoretical part here too, I should mention as well. Once we start using the frameworks and doing stuff here, a lot of this kind of goes to the back burner. But again, if you're trying to come up with your own graphics engine or work with things very raw, this is what we're basically starting from. Okay, so we have our frame, a point, which is your origin, and then our vectors. We know how to represent them. We can also have something called confusion, okay? So it is possible that we can have multiple vectors and they can still be the same. Again, this is kind of going back to the earlier point where a vector without any point information is technically the same object. So it is possible that depending on how you've defined things, that you don't know if there's any mathematical difference between, say, these two, right? So this is my point from the very beginning of the geometry lecture, that a vector without a point is just in the same entity. Once we tack on that point, then it becomes something with kind of real weight to it, in a way. So again, very high level gloss over of probably hundreds of years of mathematics to get here. But with something like this, we have a ton of flexibility. Okay? If I want to do anything to my objects, again, objects, I just change its representation, change its frame of reference, change its basis, and you can make it look like anything. Scaling, translation, rotation, this is all coordinate system trickery. We're going to do this through something called homogeneous coordinates. This is where we get into a little bit of symbolic land here, and we're going to leverage identities that we're just going to assume work for us. But basically what this comes down to is that for each of our objects, and we're going to basically talk like we're in 3D space from here on out, um, everything is going to be a four-dimensional construct for us. So we're going to have something that looks kind of like this, basically. And these symbols that you see on screen right now, these are basically the nice, pretty version of what I'm going to draw out here. So back to big me. If I'm going to define an object, so let's say, I guess anything, it's going to look something like this. We're getting this big, bad matrix. Just kind of filling in because we got a nice little solid identity matrix here. The reason why I'm drawing this out and why this is kind of critical here is that if everything we are doing is in 3D space, why do we have a fourth dimension? Is kind of the question you might want to be considering. Obviously, probably not. Might be half zoned out and bored at this point talking about math identities. But let's consider we are defining some object, and you'd say, hey, we're in 3D space. Why are you telling us we need 4D? Well, that's true. But that so this fourth one, this fourth dimension is going to be something we call our homogeneous coordinate. This extra value, this extra dimension, basically this one right here, enables everything that we are doing. Okay, none of this would work without this extra dimension. So that was on the homework. Hey, how about that? It's almost like he planned it in advance. Okay. Look at that. I even have a slide for it. So this is how we actually enable all of our matrix math to work, basically. It's called the homogeneous coordinate. Planning not possible. You think this is all random and not well orchestrated? Even my puns are calculated down to the nth degree, which is why they're so bad and dry. Basically, to enable, yes, anything that we want to do with these objects. I thought this was a dramatic improv class. It's funny, those delightful Whose Line Is It Anyway supercuts started popping up on my YouTube feed last night again. Basically, what we're using here is the correct correct way to actually do matrix math. Now, again, we have a hardware pipeline, which is basically our line to the graphics card. These things are going to use 4D math in order to do all these transformations, all the multiplications we're going to be doing. And I kept saying we're going to be getting to the point where we do matrix multiplications. This is that point. And we're going to do it in a 4x4 or 1x4 matrix, basically. So if we are looking at this now tiny array here, or matrix, if this is a point that we are representing, that homogeneous coordinate is going to be 1. For vectors, it'll be 0. So pretty much, unless if we're doing some kind of transforms here, you're probably going to see that homogeneous coordinate be 1. We'll talk about when it's not 1 pretty soon, probably on Tuesday, honestly. But I guess kind of the spoiler here, since I have it on the slide, When you start changing that W, you start changing the perspective. So we're basically changing how our objects are represented on screen. And you're asking me maybe, hey, professor, what is this homogeneous coordinate doing for us, and why are we doing all this math? Well, this is how we do translation, which means moving something from one point to another, or even it can be translating um, size and moving. Or no, sorry, translation is just moving. Rotation, getting confused by this figure. It should be just moving this thing up here. It's not a good representation there. Rotation, this is what you've done with your triangle so far, right? So let's spin something around maybe using, hey, look at those lovely math identities there. Or scaling, where you make something bigger, make it smaller, and then something else that we're going to talk about in a little bit called shearing, where basically you're kind of pulling vertices away from each other. This is just matrix math. That's all this is. And to get to these kinds of operations, I kind of hinted or explicitly said multiple times that we're just changing the frame of reference, right? This is done, again, by some basic matrix manipulations where we just change its base. Okay, so let's say we have two vectors here. So this is the same vector, but with different bases. Okay, so one of them, alpha, 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 beta, beta, beta. We have some identities here. Basically, all this boils down to is that you have one set of vectors, and then you have another set of vectors here. Okay? So we are basically just applying some common transformations here to rotate something. And again, this is all symbolic. I get that it's probably hard to visualize what we're doing here. But all what's really happening is that to change your base, in this case to rotate, we're doing a matrix multiplication. Okay, so M transposed times B equals A. So all I'm saying here is that you can write one in terms of the other, meaning that they're the same coordinate system, just slightly rotated. How is that happening? A matrix identity that we are multiplying by one and having it be the other. So this is something that we call a change of frame. So we're just kind of figuring out mathematically how we can represent one frame in terms of the other. And you don't have to go through and do, like a linear algebra type of thing where ax plus y equals b or something like that, right? These are well-known identities that we can leverage. Yeah, I'm not going to, if I was mean, I would make you sit there and do this all by hand, but we're going to, again, use these well-known transforms and just apply them here. And you might be looking at this and saying, okay, well, I've probably heard the term like quaternion and things of that nature in terms of 3D graphics programming. If you haven't, we'll get there. But these are all that type of identity, just how we move things around in 3D space. Maybe you're not a graphics person, you're just here as a flight of fancy. This stuff all exists in fields like robotics too, and how you manipulate things in the real world. I'm doing this like it's a robotic arm type of thing. But here we have two frames. Again, hopefully at this point this makes sense. Here is your origin, P0, Q0, just origins in a different frame. And then here's your vector representations. Excuse me. So these things are two separate frames of reference, where the origin for this one is here, the origin for this one is here. Yes, we can represent them as the same thing by a particular transformation. Okay. In this case, if I wanted to go from one to the other, I would have to translate this one over to here. So move this origin to this origin and then rotate it. Right, so two separate operations would have to happen for this to work out. But if I was drawing, say, a triangle at this origin, right, or it'd be a tetrahedron since we're in 3D space, if I translated it, it would look to you, on the screen here, I translate it, this thing moves, and then I rotate it. Right, that's all we're doing with this change of frame. So before I kind of glossed over this, I should probably clarify. If you're going through the slides, when we are doing our change of base, or our coordinate change, sorry, it's in 3D. Once we add on the frame, which has that origin, it goes to 4D, basically. So just want to clarify that point here. So here you see the change of origin and the change of vector. That's most of the detailed backstory that you need to know at this point. So if it's not clear, that is fine. Um, Basically, I'm asking you to take it on faith that we have all these well-known identity functions and things of that nature. And if you want to go super deep into graphics, it's absolutely worth picking them up. But we're really only concerned with applying them at this point. Okay, so we have a change of base, change of frame. Again, frame has that origin on it. Now let's look and actually see what we are doing here. Now, if you have, I know some of you have done 3D programming before, or even 2D in DirectX land and OpenGL land from other projects. Did any of you ever get into model view projection transformations with that type of stuff? Nope. Good. One thing I want to mention before I forget, completely divergent from class, well, it already started, so there's the computing club meeting, started at 5. Oh yeah, this stuff is going to take a lot to digest, don't worry. I'm going to be giving a talk on undergrad research there along with some other faculty if anybody is interested in that kind of stuff. But yeah, this information is very dense. I will absolutely 100% agree with you there. But kind of the key that you really have to draw out of this is that this is a 4x4 matrix, and everything from here on out is just going to be matrix math. Okay? So we are starting out with a object in space. Okay, so let's say we have a cube. And what is a cube for us? But, well, in this case, it's only three squares, which is 6 triangles, right? So 2, 2, and 2. We're not drawing the back faces. They are clipped out, right? They're behind, and we don't need to see them. But let's say that we have a representation of a cube here. Okay, so we have vertex, 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 vertex. That's all we need to describe this thing. If we are looking at it in a local space, that is within its current frame of reference, right? So when we define this thing, that's how it gets entered into memory. We can transform this thing to the world space with a multiplication against a model matrix. So here we start adding in perspective, things like the camera. I guess maybe I should step back here because this is probably going to be a lot to take in, like you said, Philip. We're going to have different representations here. We can have a local space specific to one object, a world space specific to all objects in your scene. We can have a view space, which is what the camera can see. And then we can also add on a clip space, which hides things that do not need to be there, or gives a little bit of perspective depending on how you're looking at it. Like, are we doing a isometric projection versus any of the other projection methods, basically? And after that, we have to translate it to what the computer screen can show. So this little flow chart that you see here, so start local, apply a model matrix, you're in world space, apply a view matrix, you're in the view space, apply a projection matrix, you're in the clip space, transform it to whatever your viewport needs, you're on the screen. These are matrix multiplications. So in 1 to 2 more, no, I think it's probably at the end of these slides, so maybe 1 or 2 more lectures because we're going to cut half short on Tuesday next week. We're basically just going to be defining what goes into these matrices. And based on that, you're going to get your nice, pretty objects on screen. All right. Might be a good place to end because I just think we're going to be getting into a lot of different stuff here. Yeah, this is probably a good place to stop. Anybody have any questions. I know, again, this was a lot to digest um, for today. Guess I'll leave you with this lovely GIF here. This is kind of a nice little view. We have two different perspectives. One, you see the duck sliding down the scene. Two, you see it rotating around. This camera lens is always looking at the object. So to the camera, this thing might look identical, right? Maybe lighting is changing if we have a world light out here, but we're kind of looking at this thing in a world-based perspective right now. But the camera lens is kind of following it as we go. So it might not actually be changing based on how it's looking coming out of the camera. Lots of nifty little things going on here. Anyway, I think what we'll do is we will end a couple minutes early there. One thing I should mention too, I pulled this up just in case you wanted a short refresher on vectors and how they can be written and translated and things like that. This is not something you need to know or memorize, but if it's been a while since you've looked at vectors, this helps you with how to draw them, how to add them, things of that nature. Again, I'm not going to test you on vector math or anything like that, but I will ask you, like what a frame of reference is and things of that nature too. So more of an extra little helper. Alrighty. Again, if you missed it earlier, homework's due tonight. Make sure you get that in. Will the midterm be short answer or multiple choice? Are we adding the delay? So two questions here. Okay. So let me answer Chris's. So the midterm will be mostly short answer. I'll give you probably one or two small programming questions on there as well. Quick question about the assignment. So let me pull up the assignment here again because I don't have it on the top of my brain. It's in Google Drive. Come on. I'm gonna make sure I answer your question correctly. Assuming everything works fine with your animated, add a delay so it doesn't update as quickly as possible. So this is the prior to the Sierpinski gasket one. So this is just the rotating. Or the moving one. Yeah, sorry. Yep. Yeah, basically I just want you to see what happens when you start adding delays into your render function. See what happens. Okay. And again, the study guide is up on, I didn't show you that. Crap, I showed my other class. I don't think I showed you guys. The study guide is up on Blackboard. So if you click exams, here's your study guide. I'll probably add in one or two, a few questions out of what we talked about today, just because you don't want to have to worry about that after the midterm. But if you want to get a start on what to study for, go ahead and check that out as well. We'll do a little bit of a review Tuesday as well towards the end of class. All right. Any other questions? Like I said, I'm going to pop over to the computing club. If anybody wants to learn about what you can do for undergrad research, I know you're all mostly seniors, but some of you might still be looking for somebody to link up with for that. I have done graphic stuff in the past for research too, so if that's a consideration. But anyway, I will see you all next time. Hope you have a wonderful day. and wonderful weekend. All right, bye everybody. Have a good one.